Welcome to this video on cooling tower performance and the psychrometric principles that govern how they work. We'll explore how to measure and understand the effectiveness of these systems. In this video, we'll start by examining key performance metrics used to assess cooling towers, like capacity, range, and approach. Next, we'll visualize the cooling process using a psychrometric chart and analyze the heat and mass transfer involved. Finally, we'll explore operational factors that impact performance, including water losses and air circulation changes. By the end of this video, you'll be able to clearly define and interpret core performance metrics like range, approach, and capacity, essential concepts for sizing and evaluating a tower. But before we dive into the mechanics of cooling towers, think about this. Why do ASHRAE engineers care more about the wet bulb temperature than the dry bulb temperature when designing a cooling tower? This is a key principle to keep in mind during this learning process. This question gets to the heart of evaporative cooling, and you'll find the answer as we explore how water and air interact inside the tower. The first metric used to describe the thermal performance of a cooling tower is capacity. It quantifies the total amount of heat removed from the circulating water. We calculate it using the water mass flow rate, the specific heat of water, and the temperature drop across the tower. This gives a direct measure of the energy rejected. The range simply refers to the temperature difference between the entering and exiting water. It indicates how much cooling occurred within the tower. Higher ranges typically imply more cooling, but they must be interpreted in the context of flow rate and system design. Finally, the approach tells us how close the outlet water temperature gets to the ambient air's wet bulb temperature, the theoretical lower limit for evaporative cooling. A smaller approach means the tower is more effective, but it also means a larger and costlier tower, and it may require to achieve that performance. This psychrometric chart illustrates a cooling process in a typical evaporative cooling tower. The process begins with warm water entering the tower at a temperature level here. As it moves downward through the field, it transfers heat to the upward moving air stream. At the air inlet, the air is relatively cool and dry, indicated here. As it absorbs moisture and energy, its temperature and humidity increase. By the time it exits the tower at here, it is warmer and much closer to the saturation. The water, in contrast, is cool as it flows downward, and its outlet temperature here is significantly lower. The difference between these two temperatures is the range, while the difference between these temperatures here is the approach. This chart visualizes both of these metrics, showing how closely the tower brings water to the theoretical wet bulb limit. Let's now consider some practical factors that impact cooling tower performance beyond just temperature. One of these factors is water loss. As water evaporates into the air to carry away heat, additional losses occur through drift. Drift are tiny droplets carried away in the airstream, and blow them, which remove impurities. All this must be compensated with makeup water. Another critical aspect is recirculation. This happens when the tower's own exhaust warm and moist air gets pulled back into the intake. Since this air has already absorbed heat and moisture, it reduces the cooling potential and undermines the tower's efficiency. Finally, in towers with multiple cells, interference can occur. That's when exhaust air from one cell affects another cell's intake. This cross-contamination disrupts a uniform performance and requires thoughtful layout and fan control to avoid performance degradation across the system. Well, here are some key takeaways from this lesson. Performance metrics like capacity, range, and approach are foundational for evaluating and designing towers. Psychrometric charts give us a powerful way to understand the process of evaporation and heat exchange in air. And finally, operational realities from recirculation to water losses must be considered when designing or evaluating cooling towers in practice. Well, I invite you to go deeper and continue learning. You can study real cooling towers, specs, and charts from vendors. They are essential tools for real-world design. Practice using psychrometric software to simulate changes in airflow, humidity, and tower geometry. And consider how local weather, especially wet wall variability, impacts tower selection and performance across different regions. Thanks for watching this lesson. In the next video, we'll apply these ideas to performance modeling and cooling tower selection.